In this chapter, we're going to examine stereochemistry. In other words, the way that the spatial arrangement or the three-dimensional arrangement of a molecule can kind of affect its chemical and physical properties. So we'll specifically look at stereoisomerism. In other words, how can we distinguish between two isomers based on their spatial arrangement or the way that they are, they sort of occupy three-dimensional space. These spatial arrangements can be pretty important in various chemical reactions. We especially see this in biochemistry. There are a lot of, of bioorganic molecules that have one version take part in a reaction or take part in a reaction differently than its stereoisomer. So, for example, to look at naproxen, okay, which is the actual chemical name for the drug Aleve, which is a pain reliever. One of its enantiomers, so one version of the molecule, is 28 times more potent than its mirror image. Okay, so just to give you a little example there. So, and there are a bunch of other examples. There are several molecules that that smell. When you look at one of the stereoisomers, they smell one way, and the other stereoisomer smells completely different. And this has to do with the receptors in your nose. The molecule that that's arranged one way fits into those receptors, and the other molecule fits into different receptors. All right. So this is kind of pretty common in biochemistry, just based on the way things like enzymes also are organized. Okay, so you can kind of see it here. For example, we have two molecules here that have all the same pieces, right? We have the same groups, but based on the arrangement of those groups, you can see that the way this molecule would bind with a receptor, it's kind of blocked if you just change a little bit of that arrangement. Okay, now that seems kind of weird, right? Because that's just a tetrahedral carbon, right? Isn't that completely sort of symmetrical, right? And by having these four different groups, that's where a lot of that symmetry is lost, or it's kind of forced one way or the other, and that arrangement starts becoming more important. Okay, so again, that even though we've got all four groups that are identical attached to the same carbon, that arrangement is what is different here, what's kind of important here. And we call these types of molecules where we have the same connectivity, and so therefore they're not constitutional isomers, but a different spatial arrangement. These are known as stereoisomers. Okay, so just to draw that distinction, if we look at constitutional isomers, remember we have the same molecular formula, and that's kind of the definition of an isomer, right? It's two molecules that have the same molecular formula, but that are different somehow. In the case of constitutional isomers, there's different connectivity. Okay, so for example, here we have hexane, right? We've got 6 carbons connected in a string, so that's a hexane molecule. And here we have 2-methylpentane. Right? Now, both of these have the molecular formula C6H14, but clearly they're not the same molecule. And this is what makes them constitutional isomers, because the way those carbons are connected together. Okay, but now look at these two molecules. Both of these molecules are 1,2-dimethylcyclohexane. Okay, but clearly they're not identical, even though all the groups are attached at the same places, right? We have a methyl group at the number 1 position, we have a methyl group at the number 2 position, we have a cyclohexane ring, yet they're not identical. Okay, and it's because of the arrangement of those methyl groups. So we have to add something to the name to distinguish between the two. Okay, and I think I alluded to this a little bit in the chapter on alkanes and cycloalkanes. This is here where we have a cis and trans designation to help distinguish between these two arrangements. Okay. Here's another example of a molecule that is kind of locked into place and has the different groups in different spatial arrangements, right? So you can't rotate around a carbon-carbon double bond like you could around a single bond. So these two carbons here are locked on the same side of that double bond, whereas here they're locked on opposite sides of the double bond, and these two molecules are not identical. Okay, again, we have this would be 2-butene, right? We have a double bond between carbons 2 and 3 for a 4-carbon alkene. We'll go over naming alkenes in a later chapter, so don't panic here. But we have to add something to the name to show that this molecule is different from this molecule. Okay, and it turns out, again, we're going to use that cis and trans designation here. This winds up being a cis 2-butene. This is trans 2-butene. But the fact remains, again, that everything's connected in the same places. It's how they're connected that is different, and that's why we have to add, we have to change the name, add that little qualifier at the beginning to help distinguish between these two. Okay, so have a look at these different molecules and ask yourself, are these constitutional isomers, are they stereoisomers, or are they just identical molecules drawn differently? Okay, so take a second, pause this video, and then we'll go through the answers. Okay, so you've had a chance to think about this, so let's have a look at these molecules and ask what is different about them. Okay, so if we look at this first example, all right, we've got 2 alcohol groups, right? Or we've got 1 alcohol group on a cyclohexane, so this is cyclohexanol. Now, over here, that alcohol group is shown equatorial, and this alcohol group is shown axial. So, at first glance, it seems like they're different, but is there a way to make an axial group equatorial and vice versa? Actually, it's kind of shown in the way this molecule is drawn. You can tell that this carbon, which is pointing downwards, is pointing upwards here. A ring flip has occurred, in other words. Okay, so these are identical molecules. Okay, these are the same molecule. Now look at these 2 examples. Right, so here we have an equatorial and an axial group. Okay, now here the 2 groups that are next to each other are both axial. Both of those alcohol groups are axial. Okay, so that should kind of give away that this is actually a stereoisomer. Okay, these groups are actually, if we had drawn this as a flat bond line diagram, these 2 groups over here on the right, are trans. One's pointing up, one's pointing down, whereas here both groups are pointing upwards. Okay, so they're cis. Okay, don't worry, we'll go into what it means to be cis and trans in a little bit. Okay, now look at this molecule over here. When you have, first of all, let's double check and make sure we have the same right number of atoms, right? So we've got 1, 2, 3, 4, 5 carbons with a double bond between carbons 2 and 3. Here we've got 1, 2, 3, 4, 5 carbons with a double bond between carbons 2 and 3. Okay, so they're definitely isomers of some sort. All right. Now the question is, are they constitutional isomers or stereoisomers? Okay, or are they? Is it just maybe it's just the same molecule drawn slightly differently? They're both identical. Well, they can't be constitutional isomers because everything's connected the same way. That double bond's in the same place, right? So the question then becomes, are they identical or are they stereoisomers? Let's look at that double bond since you can't rotate around that double bond. Notice that the double bond has the carbons coming off of it locked into this zigzag pattern. Whereas here, it's kind of a bend or a U shape, right? Because both these carbons are on the same side of that double bond. They're down here at the bottom. Okay, so keep in mind, again, that we cannot rotate double bonds. So these are locked in place here. So once again, number 3, we have stereoisomers. We have a trans and a cis alkene. Now let's look at these 2. Oops. Here we have 1, 2, 3, 4 carbons and an oxygen. Okay, so the molecular formula of this would be C4H8O. And if we look at this molecule here, we have 1, 2, 3, 4 carbons. Okay, there's 3 hydrogens here, no hydrogens here, 2 hydrogens here and another 3 here. So that's 8 hydrogens, and we've got 1 oxygen. So both of these have the same molecular formula, all right? But are they connected in the same way? Clearly not, right? We have a double bond between this carbon and this oxygen. There are no double bonds here. So these two are constitutional isomers. Things are connected differently. We don't have our carbons in a ring like we do over here. Okay? Now look at this last one. If you try naming this, that's probably a surefire way to figure it out, but you know, you haven't learned how to name alkenes yet. But basically, this is a 2-methyl-2-butene, right? And this is also 2-methyl-2-butene. Now, is this cis or trans? Because we have 2 methyl groups here, really you don't have cis or trans. There's no way to flip this and get the opposite thing. In fact, if you take these two molecules, if you take this molecule and you just flip it 180 degrees over, you'll get this molecule over here. Okay, so these two molecules are actually identical. Okay, you've heard me using that cis and trans designation quite a bit, and as I mentioned, I think I alluded to it a little bit in an earlier chapter. Basically, the word cis means same. So wherever you have your main parent chain or ring, if identical groups are on the same side of it, that makes it the cis version of that isomer. If the identical groups are on opposite sides, that's the trans version, right? Trans means opposite. So here we have 1,2-dimethylcyclohexane, but since both these methyl groups are on the same side of the ring, that's cis 1,2-dimethylcyclohexane. Likewise, here the methyl groups are on opposite sides of the ring, so that's trans 1,2-dimethylcyclohexane. Okay, we can do the same thing with double bonds, of course. Again, the key thing here is you need both groups to be identical. Okay, now please note, a group here can be something as mundane as a hydrogen as well. Okay, so even though in this example here on the left, this fluorine and this methyl group are not the same thing, we could call this trans because these two hydrogens are trans. Okay. By the way, if you get mixed up between, you know, when you're trying to decide, when we say our groups are on the same side or on opposite sides, how are we dividing our molecule? Imagine your double bond is making the border. So you're kind of extending that double bond, and that's the border of your molecule. Okay, that's what's bisecting your molecule. So if we made, you know, so if we kind of had a line going this way, whoops, oh wow, that I need to draw a little bit straighter than that. Let's try that again. Okay, so if we had, you know, basically, just imagine that's dividing our molecule. Okay, so notice that we have a hydrogen on one side and a hydrogen on the other. Okay, now here we have our two fluorines. Again, if we extend this double bond, both fluorines are on the same side of that border, and that's what makes that cis. Okay, again here, if we have, you know, here's our double bond, we extend it that way. Oops. Okay. Notice that this ethyl group and this ethyl group are on opposite sides of that border. Okay, and that's what makes that trans. So let's try another practice problem. Have a look at this. You know, pause this video and ask yourself: are these cis, trans, or neither? Okay, welcome back. Let's go through the answers. So over here we have our double bond. Okay, now you've got to look for two identical groups, right? In this case, the two identical groups are the hydrogens that aren't shown, but both of these hydrogens are on the same side of that double bond, so that is a cis double bond, cis alkene. Now let's look at this guy. Here we have two alcohol groups. They're both pointing upwards. Okay, even though one's equatorial, one's axial. Okay, they're both pointing upwards. So they are on the same side of that cyclohexane ring. So this makes it a cis isomer. Now let's look at this guy. Here we have a methyl group and an ethyl group, but we again have two hydrogens. We have a hydrogen pointing here and a hydrogen pointing down here, and they are on opposite sides of this double bond. Okay, so again, if you're having trouble seeing it, you know, you can kind of imagine that that double bond extending, and we have a hydrogen here and a hydrogen here. Oops, there we go. And they're on opposite sides of that border made by the double bond. So this is the trans isomer. Okay. Likewise, here we have one group pointing upwards, one group pointing downwards. This is trans. This example is an interesting one, and I think I kind of gave this one away earlier when we looked at this, but this is neither cis nor trans. All right, so if you look at this and you say, all right, why isn't it cis or trans? Whenever you have two of the same group on the same carbon, you're not going to be able to flip it to make its isomer. So for here, since we have two methyl groups on this carbon, this can't have a cis or trans isomer, because if we were to flip this, let's say we flipped the position of this methyl group and this hydrogen, right? And we drew this molecule here. Okay. Oops, sorry. That's the same molecule. I meant flip the methyl group and the hydrogen had the methyl group pointing upwards. So let's try that again. Let's draw that. Okay, there we go. Notice that these are still the same molecule, because I could rotate this molecule 180 degrees. I could just flip it, and when I flip it 180 degrees, I would get this molecule back again. Okay, so these two are identical. Okay, and it comes down to the fact that basically these two groups here are identical, and no matter how you flip it, you're going to get the same molecule again. All right, now beyond cis and trans isomerism, there's also chirality. Okay, this is kind of the example that I showed you towards the start of this PowerPoint when we were talking about the about drugs and their mirror images and how one can work and one might not. All right, I kind of showed you that picture of the molecule with 4 different groups on a carbon, and how those were arranged changed how that molecule was able to sort of interact with something. I think they used sort of like little box, like square and triangular and circular boxes to illustrate that. Okay, a chiral molecule or a chiral object is something that is not identical to its mirror image. Okay, so you have if you had two chiral objects, two enantiomers next to each other, they would be non-superimposable mirror images. Now, your hands are chiral. That's actually what the word chiral means. It refers to hands. It's from the Greek word for hands. If you look at your two hands and place them in front of you, then line your thumbs up to each other, you'll see that your left and your right hands are mirror images of each other. Okay, whether you hold them thumb to thumb or place your palms facing each other. Okay, but they are not identical. You can't overlap them. Okay, you can't have both of your palms facing you and have them overlap. Okay, you can only have them as mirror images, but they are non-superimposable. Okay, and that's what we mean by chiral objects. Now, when it comes to chirality, this is going to get a little bit challenging. I think especially trying to teach this over a video. I really recommend, if you haven't already done so, getting out a model kit and looking at some of this. Okay, so make sure you have a model kit out. This chapter will involve thinking in 3D quite a bit. And this is an acquired skill. It takes a while to get the hang of this. So first of all, don't be frustrated if it doesn't come to you as quickly as you'd like. All right, that's completely normal. Okay, but you do have to practice it. And what I've found with most students is using models and manipulating them and holding them and just rotating them, seeing them in front of you, allows you eventually to be able to do that in your head. But doing that in person, like you're doing that physically first, goes a long ways towards the being able to do it mentally. All right, so here's an example of two chiral molecules. So this is what we mean by chirality and non-superimposable mirror images. Okay, so these two molecules are mirror images. So we have a mirror plane here, okay, kind of illustrated with this picture over here, and you can see that these two molecules are mirror images. However, if you build these two molecules, build them the way they are drawn here as mirror images, and try to superimpose them, try to put this carbon next to this carbon here and rotate this molecule so that it sits on top of the other. You'll get two of the atoms to line up, two of the groups to line up. Two of the other groups will not. They'll be switched. Myself, basically, I used 4 different colored atoms to reflect the 4 different groups attached to that central carbon. So here we have our central carbon, and I've used different colors to represent the 4 different groups. Now, these two molecules, as you can see, are mirror images of each other. But here's what I was talking about, the non-superimposability. If I try to move this carbon over this carbon and try to get these two molecules together, I can only get 2 of the atoms to line up, or 2 of the groups to line up. The other 2 will not. So here I can get green and white to line up, but I can't get blue or red. Okay. Likewise, I could get blue and red to line up, but I won't get green and white. Okay. And there's, you know, all the other combinations. I could, for example, get green and red to line up on the 2 molecules, but then blue and white would not, and so on. Okay, so this is what I mean by non-superimposability. Even though these 2 molecules, to go back, even though these 2 molecules are mirror images of each other, they have all the same pieces, and they're all connected to that same carbon. Okay, so despite that, these are not identical molecules. They are, in fact, stereoisomers. So how can you tell if you have a molecule that's capable of chirality? Well, you want to look for what's called a chiral center, also known as a chirality center, or a stereo center, or a stereogenic center. And it's basically a carbon with 4 different groups coming off of it. Now, what do I mean by groups? These could simply be atoms, or they could be groups of atoms. They could even be pathways in the case of a cyclic compound. So let's look at examples here. Okay, so over here, this carbon over here is chiral. What are the 4 different groups coming off of it? We have a methyl group coming off. We have coming off to the left. Whoops, there's a methyl group. There's a chlorine coming off of it that's pointing towards you. What's not shown is a hydrogen over here that's pointing away from you. We have an ethyl group as well to the right here. So that's 4 different groups: a hydrogen, a chlorine, a methyl group, and an ethyl group. Look at this group, this chiral carbon over here. We have an ethyl group with its 2 carbons, a propyl group with its 3 carbons, an alcohol group, OH, and a hydrogen which is not shown, that's pointing away from you. Again, those are 4 different things. Look at this example here now. This one's a little trickier because here, these, you might be tempted to say, well, isn't this the same group? Isn't this all one thing? All right. Well, first of all, our bromine and hydrogens, of course, are different. But if these 2 are the same, that would be achiral. However, look at the pathways. Now, what do I mean by pathway? When I go down this path away from that carbon, I'll go 1 carbon and then another carbon, and notice I have only a single bond here. If I go down this pathway, I've got 1 carbon and then a double bond. Okay, so that immediately makes this side of the molecule different from this side. Okay, this would also be a different pathway if we had another group branching off over here or over here. And it wasn't, you didn't have an equivalent branch on the other half. I also realized I just used the word achiral earlier. I just want to clarify the word achiral, okay, that's with the letter A before the word chiral, that means not chiral. So when I said that this, if these 2 pathways were the same, if they're identical, so that this was sort of one identical group, that would be achiral. I meant that it would be not chiral. It's the difference between the 2 halves of this of this ring that make it chiral. Okay. So sorry for the confusion there. I realize this is the first time. This might be the first time you're hearing the term chiral, and just realize the prefix a in front of it means not. Okay. Okay, so let's have a look at some examples, and so feel free to pause this video and see if you can figure out if there are any chiral centers here. So look at each of the carbons and ask yourself, are there 4 different groups coming off of this carbon to make it chiral? Okay, so welcome back. Hopefully you found, different chiral carbons. So to pull up the answer, here we go. So in this case, none of these are chiral, right? So if you look at any of the carbons, really any of the carbons, as soon as you see 2 of the same group on your carbon, you know that it can't be chiral. It is achiral. So all of these carbons on your cyclohexane whoops, going back there. So all of the carbons on your cyclohexane have 2 hydrogens on them that aren't shown, right? That automatically makes them not chiral centers. It makes them achiral. But if we look at this carbon over here, this might have some potential, right? You could say, all right, that oxygen is different from this hydrogen. Now, what about these 2 carbon pathways? Well, they wind up being identical. Okay, so no matter where you go down this pathway, and in either direction, you would trace the same path. You've got a carbon, CH2, 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 and so on. CH2, 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 and so on. So that's why there are no chiral centers in this molecule. Okay. For all the other ones marked with an asterisk, there's going to be 4 different groups. Okay, so it's a little bit easier to see in these ones that aren't rings. So for example, here we've got a methyl group, and then this isopropyl group is different from this sec-butyl group. Okay, and of course there's a hydrogen that's not shown. That's the 4th group. Likewise here, got a methyl group and ethyl group, and then this is something completely different, and there's a hydrogen which is a 4th group. Okay, and you can see that for all of these, hopefully. Right? This one might be a little bit tougher to see, but it's kind of like the same scenario here with this carbon that could have had some potential to be chiral, but had 2 identical pathways. Here, the pathways are not identical. Okay, because here, let's say we're looking at this carbon over here, we've got our OH group, we've got a hydrogen, which is not shown, but now look at the 2 pathways going off of it. Over here, you have a carbon with an OH group attached to it. Over here, you have a carbon that doesn't have an OH group attached to it. And so clearly this side of the molecule is different from this side. And you have a similar, similar setup on this carbon that makes it chiral as well. So when we have chiral centers in our carbons, or we have 2 chiral molecules, we can describe these as enantiomers. Okay, we'll see a scenario where it's possible to have carbons with chiral centers that are not enantiomers, but basically for now, if you have 2 non-superimposable mirror images, these 2 molecules are enantiomers. Okay, so to draw an enantiomer of a molecule that's given to you, you simply have to draw its mirror image. Now, there's 2 different ways to draw that. Okay, so you could basically, the way they show it here is they literally just draw the mirror image, right? They draw the just that same molecule in reverse, imagining a mirror plane over here. The other way to do this involves flipping a wedge and a dashed wedge. So a solid or a dashed wedge, flip it to the opposite side. So for example, I could have drawn this molecule as the same molecule, but instead of using a solid wedge for the chlorine, I would use a dashed wedge. Okay? Now, this molecule, if I were to rotate it 180 degrees, it would look like this. Okay? Because instead of this chlorine sticking into the screen, when I rotate 180 degrees, it would stick out towards us, and we'd have a solid wedge here. But this ethyl group would be on the left, and this methyl group would be on the right, instead of on, the methyl group on the left and the ethyl group on the right. Okay, so that's kind of what I mean by flipping, you know, a wedge or a solid wedge or a dashed wedge. Okay. So here, I think earlier at the start of this chapter, I mentioned examples with biochemical pathways, right? Here's an example of one of those. Because your nose has very specific receptors where one enantiomer might fit into, might interact with one receptor and the other enantiomer might react with another receptor. Here is the molecule carvone. So one enantiomer here smells like spearmint, the other one smells of caraway seeds, even though they are otherwise identical molecules. It's just that flipping of that one chiral center that causes this molecule to smell differently. Okay? So these two molecules, again, are not identical, right? We've seen that with all the other stereoisomers, with our cis-trans isomerism as well. But so just like with cis-trans isomerism, we need to have a word or a prefix or something that helps us distinguish between the two names for these molecules, right? We can't just call them 2-chlorobutane because while they are both 2-chlorobutane, they're not the same molecules. We need something to distinguish them. So to do that, we use what's called the Kahn-Ingold prelog system, which uses an R or S designation in front of the molecule to help denote which enantiomer it is. Okay, now for the Kahn-Ingold prelog system, you have to look at the arrangement, okay, of these groups around that chiral carbon. Okay, so to do this, we're going to assign the groups priorities. We basically give them priorities based on atomic numbers. The higher the atomic number of the atoms involved, the higher the priority, and obviously the lower the priority. So hydrogen, which has an atomic number of 1, as the simplest atom we can get, that always has a priority of 4. It has the lowest priority, it's the lowest ranked of the 4 atoms attached to your chiral carbon. Okay, so what you want to do then is you want to sort of point that lowest priority group away from you. If you're doing this with a handheld model, I recommend sort of holding it by that lowest priority group, kind of like a flower. Now the other 3 groups are pointing towards you. Okay, if you can point at them in order of priority, from first priority to second priority to third priority, look at whether your hand is moving clockwise or counterclockwise when you do that. Okay, if it's moving clockwise, it is an R designation. The R stands for recto, or right in Latin. If you find that your hand's moving counterclockwise as you follow from priorities 1, 2, and 3, that is S, or sinister, or left in Latin. Okay, so here's an example, right? Here we have a chiral carbon with a hydrogen, a chlorine, an oxygen, and a carbon coming off of it. So if we organize that by atomic number, chlorine has the highest atomic number, right? That's an atomic number of 17 compared to 8 for oxygen, 6 for carbon, and 1 for hydrogen. So you can use your periodic table here to figure this out, right? So basically, the way to write this out then would be to point that hydrogen away from you and see which order the your groups are following, whether they go, when you're going from chlorine to oxygen to carbon, whether that's going clockwise or counterclockwise. Now, the way I just did it there looks like it's counterclockwise, but this is actually not shown the right way for you. This hydrogen is pointing towards you, so that's actually backwards. This would actually be an S designation. Okay, so yeah. Anyway, go ahead and try out this molecule here and look at the groups attached to it and see if you can prioritize them. So you can see that we have a chlorine with an atomic number of 17. We have a hydrogen here that's going to be atomic number 1, so that's probably going to be the lowest priority, so that'll be a priority of 4. Now here we have 2 carbons. Okay, so the question is now, how do we prioritize that? Well, you want to look at what's attached to those carbons and use those as tiebreakers. This carbon here has only hydrogens attached to it. Okay, and each of those have have atomic numbers of 1. This carbon has 2 hydrogens, yes, but it also has a carbon. So that kicks it up higher in the tiebreaker, and this is given the rank of 2. Okay, so it goes chlorine, then this carbon, and then the hydrogen that's not shown. So just to give you a visual on this, here's what I mean by holding this like a flower, right? So here I've made a molecule, and I've kind of, just to help designate priorities, I'm going to use just the American colors here, red, white, and blue. So imagine that this unlabeled atom here is a hydrogen, so it's lowest priority. And let's imagine that it goes in order of priority. Red is number 1, white is number 2, and blue is number 3. Okay, so red, white, and blue in that order. So you hold your molecule by its lowest priority group, in this case the hydrogen. Okay, and then you point the remaining 3 atoms towards you. So here's that molecule that I was holding up earlier. Now, if I were to follow along with those in order of priority, so remember, red is the first priority, so that's probably the highest atomic number of the 3. Then comes the white one, then the blue one. Now here, if I follow that arc, that is the R designation. I'm going clockwise when I draw that. So if I designate this as priority 1, priority 2, and priority 3, okay, I am going clockwise, and that is the R designation. Oops. Okay, that's an R designation. Now, let's try the mirror image of this. So, the mirror image of this looks like that. If I assign priorities, this is priority 1, red, white is priority 2, and blue is priority 3. Now, if I go in that order, going from red to white to blue, so priorities 1, 2, and 3, notice that now I'm going counterclockwise. And so that is the S designation, okay, or sinister. So that's basically how you would use a handheld model to tell the Kahn-Ingold pre-log system. I mentioned that having a model kit on hand is very useful for this reason. This is also, again, why you are allowed to use a model kit on your quizzes and exams, right? So please do take advantage of that. That being said, if you don't have one handy, or you want to eventually get to the point where you don't need to rely on a model kit, it's possible to do this with your drawing as it is on paper and figuring out accordingly. I mentioned earlier that the way this molecule is drawn, it is drawn kind of incorrectly. That hydrogen's pointing towards you instead of away from you, right? So what you need to do is get that hydrogen to point away from you. So instead of pointing towards you. So you, in other words, need to rotate this molecule 180 degrees so that it's pointing away instead of towards you. Well, what happens effectively is the chlorine, which is pointing away from you, now would be pointing towards you, as well as having that hydrogen pointing away from you. But in doing so, if you're rotating this 180 degrees, groups 2 and 3 also rotate. So please note that they also switch positions. So keeping that in mind, the shortcut here is that whenever you flip a molecule around, just realize that you are rotating the solid and dashed wedges. Those are flipping positions, but you're also flipping positions on the things that are just in the plane here. So with that in mind, see if you can practice that. Go ahead and try to assign priority groups, and then try and arrange this so that the lowest priority group is pointing away from you. Okay, so the lowest priority group, which you can't see here, is the hydrogen that's on this carbon. Okay, so here's your chiral center. That hydrogen is pointing towards you because that nitrogen is pointing away from you. You want to rearrange this molecule so that that hydrogen is pointing away from you and that nitrogen is pointing towards you. So notice that you have to flip the the solid and dashed wedges here. So the hydrogen flips back here, the nitrogen flips front here. But you also have to flip these two atoms that are in the plane. So this oxygen and this carbon have to flip. You've got to essentially rotate around this molecule, and so it flips this way. Okay, technically these two carbons have also flipped position when you rotate around the rotational axis that's going this way, but you can't really tell that because they're both CH2s. Okay, and then I kind of pointed this out earlier when I showed my handheld model, but basically once you've got that lowest priority group pointing away from you, just look at the order in which groups 1, 2, and 3 are arranged. If it's counterclockwise, it's S. If it's clockwise, it's R. So with that in mind, go ahead and look at these examples and see if you can designate them as either R or S. Feel free to build a model if that helps. And again, you don't have to build the entire model. You can just assign atoms like I did. So for example, for this first one, I could give my chlorine a red atom. I could give this methyl group a white atom. I could give this ethyl group a blue atom, right? Really, to use the earlier designation, if I'm doing 1, 2, and 3, really it's, I guess, the ethyl group would be the white atom because that would have second priority after the chlorine and before the methyl group, which has third priority. But anywho, so feel free to pause the video here and see if you want to try this out and figure out whether these are R or S designations. Okay, so here are the answers. Okay, so this first one is relatively straightforward because that hydrogen is pointing away from you. Okay, so if we go chlorine, ethyl group, methyl group in orders of priority, so I can probably draw on this to make this a little bit easier to see. So there are hydrogens pointing away from you, so that's already back there. So chlorine, ethyl group, and methyl group, right? And you guys hopefully will remember why that is. Right, the tiebreaker here is this carbon sticking off this carbon that gives it a higher priority than this carbon, which only has hydrogens attached to it. So if we connect those three, notice that we are going clockwise, and that's why it's the R designation. Now for this molecule, again, if you didn't build a model, you wanted to try this out with the way it's drawn. Remember, you want the hydrogen that's not shown here, that's got a solid wedge that's pointing towards you, you want that pointing away from you. Okay, so you could draw the other molecule. You could draw this with the hydrogen pointing away from you and flip everything like they did earlier, and then assign priorities. The other way to do this is to remember that this hydrogen is facing the wrong way, and then realize that your answer is going to be backwards. Okay, so when you assign priorities here, remember your oxygen has top priority because it has the highest atomic number, then the nitrogen, then this carbon, right? So looking at the way it's drawn here, you'd say, oh, that's counterclockwise. It's going this way. But remember, we're looking at this backwards. So really, if we were on the other side of this screen looking at this molecule, it would look like they were arranged in a clockwise fashion for us. And that's why it has the R designation. Okay, similarly here, we have a hydrogen that's not shown that's pointing towards you. So again, if you want to flip this molecule and try this out, or if you want to imagine you're on the other side of this molecule and the answer is backwards, you would see that this is an R designation. Okay, so if we look at the atoms that are attached here, here we've got a nitrogen, here we've got a carbon, and here we have another carbon. Nitrogen has priority over carbons, so that has the number 1 designation. These two carbons Out of these two carbons, this carbon's connected to oxygens, so that's second priority, and this one only has hydrogens attached to that carbon, so that's third priority. Okay, so even though we're looking at it backwards and it looks like it's going counterclockwise, remember it's, we've got to look at it from the other perspective where that hydrogen's pointing away from you, and so that's why it's actually clockwise. All right, so what do we do when we have tiebreakers? We've already looked at this in the case of that methyl group and the ethyl group, right? If you have only low priority atoms attached to something and the other group has higher priority atoms attached to that group, that would be a tiebreaker, right? But it isn't so much a total number of atoms or anything like that. You kind of have to go in order. You've got to look at what's attached in case of the two immediate atoms in your group going away from your chiral center, and it's only if those are tied that then you move on to the next carbon over. Okay, so for example, now here these two carbons are tied with having a carbon and two hydrogens attached to them, so we move one carbon away. This carbon has two carbons attached to it and a hydrogen, whereas this carbon has only has one carbon and two hydrogens attached to it. So that's why the one with two carbons attached to it wins. Now, and please note again, this is not the sum of the atomic numbers, right? So you kind of have to, what might be a better way to look at this is to rank these atoms in order of priority, of attachments in priority, and just go down the line and do a head-to-head battle between what's attached. So here we have three carbons attached. Here we have an oxygen and two hydrogens, which aren't shown. And the oxygen's always going to beat a carbon. So that's why this has a higher priority. What do you do if you have a double bond? A double bond counts the same as if you have single bonds to two of that atom. So here we have a carbon with a double bond to an oxygen. That lists oxygen twice in our tiebreaker list. Okay, with that in mind, have a look at this molecule here and determine if it's R or S. And you're going to use some of these tiebreaker rules when designating, differentiating between this carbon and this carbon. Okay, so please note this is your chiral center here in the middle. Okay, so hopefully you've taken a crack at this, and you've probably realized the hydrogen that's attached to our chiral carbon is pointing away from us, so that's going to make determining the R and S designation a little bit easier. Chlorine, of course, has the highest priority. Out of these two carbons, though, it's the carbon on the right that's going to have a higher priority. It's effectively bonded to, well, in terms of tie-breaking purposes, it's bonded to three other carbons. We count this double bond to a carbon as two bonds to carbon. Okay, whereas this carbon over here is bonded to two carbons and a hydrogen. Okay, and so that's why it goes chlorine, this carbon on the right, and then this carbon on the left. That's a clockwise rotation, and that's an R designation. Okay, so like I said, you can, flip two pairs of groups to give you the same molecule flipped over. You can kind of use that same approach if you want to draw the enantiomer of a molecule. If you flip one group and not the other, or one pair and not the others, you will make the enantiomer. Okay, this is kind of what we did earlier when I showed you that alternative method to drawing a mirror image, where I said, oh, just flip the solid and dashed wedges. You can see that's what they're doing here. We're keeping atoms 2 and 3, or groups 2 and 3, in the same configuration. Okay, we're not flipping 2 and 3. But if we flip 1 and 4, notice that 1, which is on a solid wedge, is now on the dashed wedge, and vice versa. 4, which is pointing away from you, is now pointing towards you. Okay, but notice that 2 and 3 are still in the same order. Okay, so that's why the designation has changed now between R and S. Okay. So, so with that in mind, you can kind of also use those sort of tricks to, with while manipulating a 2D picture on paper to visualize a 3D molecule. If that helps you in terms of trying to rearrange things to try and get a um, a Kahn-Ingold prelog model where that lowest priority group is away from you, that works as well if you don't have a model handy. Okay, so you can see here, this is an example where our lowest priority group is in the plane, right? It doesn't have a dash or a solid or a dashed wedge. So we've got to do a little bit of finagling to try and get it all the way back here where it is a, that low priority group's pointing away from us. You can see here that they've kind of flipped multiple groups to try and get that to work. Okay, so just as a summary, remember for the Kahn-Ingold prelog system, identify your 4 groups attached to your chiral carbon and assign them priorities based on atomic number, using tiebreakers if you need to, and then having the lowest priority group pointing away from you. So hold it like a flower if you've built a model for it. Look at the other 3 remaining groups, and going from priorities 1, 2 to 3, determine if you were moving clockwise or counterclockwise. If it's clockwise, it's got an R designation. If it's counterclockwise, it's got an S designation. Okay. Now, when you want to show this in our IUPAC name, we write the designation at the start of the name. We put the RS designation in parentheses and just add it to the front of the name. In addition to the parentheses, please note the dash, or the hyphen, that separates out our designation from the rest of the name. Now, what do you do if you have more than one chiral carbon in your molecule? Well, we're going to use our same locants that we would normally assign in our molecule and just write them with their designation, their R or S designation next to the locant. And then we'd separate them with a comma, like we'd separate any pair of numbers. Okay, so in this case, notice that we've numbered this going from left to right with this alcohol group on the number 2 carbon and this methyl group on the number 3 carbon. So this is carbons 1, 2, 3, 4, 5. So since this number 2 carbon has an R designation and this number 3 carbon has an S designation, we just write it 2R, 3S in our parentheses. Okay, you will list these chiral carbons in order of, numerical order, basically, when you're writing this out. Okay, so even though this is in alphabetical order here, and not the detriment, but I guess the ignoring of numerical order, here we go strictly in numerical order. Because enantiomers are so similar, even though they're not the same molecule, they're not identical, they are still really, really similar, right? The problem with this then is that it's really hard to distinguish them. A lot of their properties are near identical. Okay, so for example, here's R and S carvone, right? 2 enantiomers, one smelling like spearmint, the other smelling like caraway seeds. So clearly they're different, right? From smell, you can do that. But if we were trying to measure their physical properties, because it's probably not always a good idea to use smell alone to distinguish between molecules, if we try to use, let's say, melting point or boiling point to distinguish them, which is how we normally distinguish other molecules from each other, that doesn't work here. They have the same melting point, they have the same boiling point. So that doesn't, that's not a good way to distinguish them. You can see that this also becomes an issue when it comes to purification, right? If you want to distill a liquid mixture, well, if you have 2 liquids with identical boiling points, they're not going to be separated, even if you use fractional distillation. Okay, so if you want to identify something based on its melting point, like we do in lab, if you take a sample of carvone and get a melting point of 25, We're like, great, is that R or S carbone? They're both 25 degrees Celsius. The melting point doesn't tell you anything. So that's that can be a problem when it comes to enantiomers. Okay, so we've got to think about other ways we can distinguish them. And one of these ways is how these enantiomers affect light, specifically plane polarized light. That is light that is sort of filtered so that the waves are traveling in one direction, okay, or sort of um, at one angle. All right, so basically light travels in waves, right? This is going into physics, but and there are multiple ways you could describe light, but one of the earliest ways to describe it is seeing that it is a wave. Now, light being electromagnetic radiation has has an electrical field and a magnetic field, right? So its waves are accordingly aligned with those, okay? But these are orthogonal or perpendicular to the direction that the light's moving. Okay, so if we can sort of force the light to only go one way, or rather we can filter it so that only the light going the way that we want it oriented gets through, we call that plane polarized light. Okay, so to do that, we use a sort of set of slits that are aligned in one direction. So if you have a mixture of orientations of light and you pass it through this filter where all the slits are only in one direction, all of the light that goes through is also in that one direction. Okay? Now, if you have something in between here that deflects light or bends it, we can use a second filter, and looking at the way that we angle it, we can figure out how much that light has been angled, right? How much has been deflected or bent. So in this case, there's nothing here deflecting the light. So the slits over here are lined up with the slits over here, showing a deflection of 0. But if we had a sample here that did deflect light, we might have to change this accordingly, but we could use that rotation to measure the angle of deflection. So here's what I mean. If we have a sample of our material, okay, our enantiomer is going to deflect light in a particular direction. And of course, we can use this then to figure out what that angle is. Here's the really cool thing. While one enantiomer deflects light in one direction, the other enantiomer deflects light in the opposite direction. Now, there are other factors besides the enantiomer used that affect how much the light gets deflected. It might depend on the concentration of your sample. It might depend on the path length of the light, like how far the light's traveling, and things like that. So if we take that into account, we get what's called a specific rotation. Right? So if we have 1 gram of a compound in 1 milliliter of solution with a path length of 1 decimeter, we can, basically get a standard there for optical rotation that we call specific rotation, and we designate that with a Greek letter alpha. Okay. Now, oftentimes when you're reporting the specific rotation, because things like temperature and wavelength of light can also affect this rotation, oftentimes you report that data by listing the temperature and the wavelength. This, represented here with a t and a lambda, respectively. Okay, so for example, here we have a specific rotation for R2-bromobutane. It is recorded at, using at 20 degrees Celsius using the D line of the sodium spectrum. Okay, and so you can see here that this S enantiomer also has the same parameters. So that's not really important. It's just to show that, okay, these are identical conditions is all, and so we can compare them. Now, here's what I mean by enantiomers deflecting light in opposite directions. With the case of the R enantiomer, it deflects light 23.1 degrees to the left, whereas the S enantiomer deflects at 23.1 degrees to the right. Now, that's what the plus and minus signs refer to, whether light's being reflected to the left or right. However, notice that this R enantiomer, doesn't R stand for right or recto? Doesn't S stand for sinister or left? Why is the light being deflected the wrong way? Does everything get deflected the wrong way? Well, it turns out that no, it can deflect, basically some R enantiomers deflect light to the left, some deflect it to the right. Sometimes it depends on the parameters that you run the experiment at. Okay, one enantiomer might behave one way at a particular temperature, might behave differently at another temperature. There is no correlation, there's no relationship between R and S configuration of molecules with the levorotatory or dextrorotatory rotations of the light in the experiment. Okay. To introduce those terms, dextrorotatory, dextro also means right. So that positive sign means that light is deflected to the right, kind of clockwise. Levorotatory means kind of deflection to the left. That's represented with that negative sign. Okay. And again, as I pointed out, there's no correlation here, not even within one molecule. You can see here this molecule that's levorotatory at 20 degrees Celsius is dextrorotatory at 100. Okay, and so there's no correlation between the fact that, if you look at this and say, oh, is this R, is this S, you can't really connect that with it being, plus or minus, because it obviously can be either. Okay, so when it comes to determining R and S designation, we can figure that out from the molecule itself, okay, using the Kahn-Ingold pre-log system. When it comes to optical rotation, that plus or minus, the only way to do it is experimentally. Okay, so if you ever get a quiz question that says, here's an R enantiomer, is it going to be levorotatory or dextrorotatory? The correct answer is, we don't know. Okay, and it's okay here to say that you don't know because it's impossible for you to tell. All right, the only way you could figure it out is if the question gave you some experimental data. Okay, so a racemic mixture, and it's another term we want to introduce here that you may not have heard before. The word racemic refers to an even mixture of two enantiomers. You have two equal amounts of your two enantiomers. In this case, the deflection of light cancels itself out. So you wind up having a deflection of 0. Your light doesn't get deflected at all. Okay. With that in mind, though, what can we glean from this experimental evidence? Well, we can use experimental data to figure out the enantiomeric excess, or percent %EE, of a sample of a mixture of two different enantiomers. Or vice versa, if we know the enantiomeric excess, we can then figure out what the deflection of light ought to be. First of all, though, what is enantiomeric excess? How do we calculate it? As the name suggests, it's the excess of one enantiomer. So for example, if you have a 70% mixture of your R enantiomer, and the remaining 30% of your mixture is the S enantiomer, well, the enantiomeric excess is 40% of the R enantiomer. Right? So 70 minus 30 is 40%. That means you have 40% more of your R enantiomer. So, how is this related to our alpha, to our basically our specific rotation? Well, you want to take into account which your when you look at your enantiomeric excess, which is your excess enantiomer, right? R or S, and you want to look at the alpha of that pure enantiomer. you then want to look at the alpha that we observe experimentally for your mixture. That percentage, so times 100, will equal your enantiomeric excess. Oops. So let's try a problem out here. So we're told that this mixture has an optical rotation of 4.6. Okay, so keeping in mind that and that's positive 4.6. So just that positive sign alone, that levorotatory excess, tells you probably have more of this S enantiomer. Okay, and so we know that the basically we have our observed alpha 4.6, our pure enantiomer alpha of positive 23.1. What is that percentage going to be? Well, 4.6 divided by 23.1 times 100 is 20%. So we have a 20% enantiomeric excess of this S enantiomer. So just to summarize our different relationships here, we have isomers where we have molecules that have the same molecular formula but are not identical, out of which we have constitutional isomers where atoms are connected differently. And then we have stereoisomers where they have the same connectivity but are still not identical. So out of these we have enantiomers, which are non-imposable mirror images, non-superimposable mirror images. And then we have what are called diastereomers. These are not mirror images, but are still stereoisomers. So an example of these could be cis-trans isomers. Cis-trans isomers are diastereomers. So for example here, we have cis-2-butene and trans-2-butene. These are not mirror images of each other, right? There's no way we could draw a mirror plane to reflect this molecule into a form of this, okay? But they are still stereoisomers, so that makes them diastereomers, okay? So diastereomers can also include chiral molecules that have more than one chiral center, where you have a reflection in one chiral center but not the other. You'll see a lot of these diastereomers, especially in molecules like carbohydrates, where there are lots of chiral centers. We'll talk way more about this in chapter, or I forget the chapter number, but basically at some point late in Chem 204 when we start getting to a little bit of biochemistry. Okay, with that in mind, here is a molecule. This is 2-methyl cyclohexanol. All right, so we've got a methyl group and an alcohol group on our cyclohexane. So let's look at the stereochemistry of this. So look at each of those carbons. So for example, the carbon that's connected to your alcohol group is going to be a chiral carbon. You've got a hydrogen, you've got an alcohol group, and then this pathway is different from this pathway because this pathway down here has a methyl group sticking out. Now, likewise, this carbon is also chiral. You've got a methyl group, you've got a hydrogen, which is not drawn, and then this pathway is different from this pathway because the pathway going up here has an alcohol group sticking off of it. Okay, with that in mind, ask yourself, how many different ways can we draw this molecule if we take into account stereochemistry? So think about the cis-trans relationship of this methyl group and this alcohol group. Okay, so if this is pointing up and this is pointing down, right? Or if this is pointing up and this is pointing up, and so on. Think about how many different combinations you can make. And then, once you've done that, ask yourself, are these combinations enantiomers or diastereomers? So this is not the same example as back there, but here we have 3 different substituents, right? And you can see some different examples here of them, of the different groups being, pointing towards you and pointing away from you, or pointing up or down, depending on how you look at it. And so you can see that here, when you flip all 3 chiral centers. So here we have up, up, up. Here we have down, 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 right? Uh, these are enantiomers, but any combination of one molecule with one in another box, those are going to be diastereomers. Okay, they have the same chiral centers, but because they aren't perfectly reflected, not all three chiral centers are reflected, that makes them diastereomers and not enantiomers. Okay, it's only when all three are flipped exactly that you've got, you know, the enantiomer pair. So with that in mind, here are the combinations with the 2-methyl cyclohexanol, where we can see how to arrange our OH group and our methyl group and see how many different ways we can do that. So for example, here on the left, we have our alcohol group pointing away from us. You could think of it pointing downwards. And we have the methyl group pointing towards us. So let's say that's upwards. Okay, so we have a down-up orientation here. Here we have an up-up orientation. Here we have up-down. And here we have down-down. Okay, and here we've got these molecules drawn slightly differently to show you what they look like in 3D. Though maybe it's a little bit easier to see this in, in this bond line diagram using these wedges. Okay, now how are these connected as enantiomers or diastereomers? Here are the different combinations. Okay, so here are these two molecules. Okay, actually, if I go back a slide, that's this molecule here, and this molecule is just flipped 180 degrees. Now, when you flip it, this molecule, this OH group, winds up, instead of pointing towards you, winds up pointing away from you. Okay, when you flip it 180 degrees. Likewise, this methyl group, instead of pointing away from you, is going to point towards you. So that's what's happening here. So notice that by having them pointing to the left, this methyl group is pointing towards you, this OH group is pointing away from you. Notice how these two molecules are mirror images of each other. We could draw a mirror plane here, and notice that these two are reflections of each other. That's what makes them enantiomers. Okay. Now, on the other hand, these two molecules are diastereomers. Okay, and likewise, these two molecules are diastereomers. Here are the other three combinations. These two molecules are enantiomers. Notice again, we have that mirror image. Okay, and here, these are diastereomers and these are diastereomers. Okay, so it's only the cis molecules that can be enantiomers of each other and the trans molecules that can be enantiomers of each other based on just the way their reflections work, right? So even though, like, as enantiomers, one's up up, the other one's down down, that again allows them, that perfect reflection of those two chiral centers is what allows them to be enantiomers. But as soon as you have only one chiral center changed but not the other, now those are diastereomers. So for example, here we have, let's say, an up-down. Again, notice that this molecule is flipped over 180 degrees. That's what I'm calling this down, even though it looks like it's up. So even though these have different chiralities, if one's R, the other's S, these two are the same. Okay, so if I flip this 180 degrees, this would be a solid wedge, just like over here, with that OH group pointing off in this direction. And that's what makes that a diastereomer. So with that in mind, the key thing to realize with chiral centers is that you can have two possibilities, right? R or S. Well, with the number of chiral centers, you then increase the number of possible stereoisomers you can make. That being said, if you do a calculation using that binary, using 2 to the power of n, where n is your number of chiral centers, please note that's the maximum number of stereoisomers. It is possible to lose stereoisomers through mirror planes within your molecule, through reflection planes. We'll get into these in a little bit. These are what are called meso compounds. Okay, so anyway, first let's practice this concept. Let's look for the number of stereocenters the number of chiral centers in this steroid over here, this cholesterol, and ask ourselves how many different ways could we flip these centers to get how many isomers. Okay, what's the maximum number of isomers we can get? So first step here is to count the number of chiral centers. All right, so if we were to count those out, we'd basically have, well, this is a chiral center here. This pathway is different from this pathway. Again, you've got a hydrogen and an OH. That's one chiral center there. This is a chiral center. You've got a hydrogen, or sorry, not a hydrogen, a methyl group. And then this pathway, and this pathway are all different. So that's the second chiral center. This is a chiral center. Okay. You can again see the three different pathways in the hydrogen. This is a fourth chiral center, fifth one, sixth one, a seventh one, and an eighth one. So this would have 2 to the 8th possible stereoisomers. So 2 to the power of 8 is 256 different isomers. So there's 256 different combinations of those 8 chiral centers that we could make. Now keep in mind that's a maximum number. In reality there might be fewer than that, depending on how whether it's possible to actually flip a chiral center to have an R and S designation. Okay. All right. So what do I mean by that? Well, basically, with an even number of chiral centers, there is a possibility that there's some canceling out of enantiomers, of chirality, okay, due to the presence of a mirror plane. Okay, so let's look for our chiral centers in the example here. I think let's have probably figured out that this carbon over here and this carbon here are our chiral centers, right? We have a hydrogen, a methyl group, and then this pathway and this pathway are different because this pathway has a methyl group branching off. And the same over here. This is a chiral center and this is a chiral center. Okay? But if we look at the molecule on the left, while that trans molecule is capable of having an enantiomer, the cis molecule on the right is actually achiral. Okay, it's achiral, meaning it is not chiral. The reason for this is that there is a mirror plane within the molecule. Okay, and that is what causes its mirror image to be identical. So if you try to build the mirror image of this molecule, you'd realize it's the same molecule. Okay, so something to watch out for. We call this these compounds that have a plane of symmetry within them, thus canceling out their even number of chiral centers. Those are called meso compounds, okay, or meso. But yeah, basically that's how you would identify them. Just see if there's a mirror plane that you can draw somewhere in the molecule. So, for example, here is our cis 1,2-dimethylcyclohexane. Okay, and here's how you can prove that it's the same molecule. So here's its mirror image. If I flip it over 180 degrees, it looks like this. So these two methyl groups which are pointing towards us are now pointing away from us. Okay, but now if we rotate it around this axis here in the middle, so we kind of flip it, along this rotational axis that's going, running like east-west here. Okay, so we're rotating like this carbon up here and this one down here, for example. Now, instead of having these groups pointing away from you, they start pointing towards you. So this group that's pointing away from you up here becomes this group that's pointing towards you down here. And notice that it is identical, it's the same as the original molecule, okay, that we had as its mirror image. Okay, so yeah, like I said, you can either play around with the molecules that way, or just look for a mirror plane. That also is a quick way to figure out if you have a meso compound. All right. So if we were to draw all four isomers of the 1,2-dimethylcyclohexane, so this is kind of similar to the exercise we did with the 2-methylcyclohexanol, except now instead of an OH group here, both of these are methyl groups. Okay, and so we're going to cut down our chirality. This is an example of what we kind of talked about earlier about the maximum number of stereoisomers and how that's a maximum number. In reality, it might be lower. Okay, so with the case of 2-methylcyclohexanol earlier, we had two chiral centers, and 2 to the power of 2 is 4, right? 2 squared is 4, and so there were 4 different molecules we could draw, right? Well, in this case, again, we have 4 different molecules we can draw, but we'll quickly find that 1 and 4 are identical, as we saw in a previous slide, right? Here, so here's molecule 1, here's molecule 4, but it's the same thing if you flip it 180 degrees. So there we go. So 1 and 4 are the same thing. So even though mathematically it seems like there's 4 different ways to draw this, there's actually only 3. Only 1, 2, and 3 are identical are unique molecules. Okay. Have a look at these two molecules. Ask yourself what their relationship is. Okay, so take a second, try this out. Now, you could try manipulating this as, using a model. You could try drawing out, just trying to manipulate it on paper. That being said, just like with constitutional isomers, where the foolproof way is to try to name your two molecules, and if they have the same name, they're identical. In the same way here, if we can look at our chiral centers and designate them as R or S, and then compare the R and S designations of the chiral centers in our other molecule, that might also be a foolproof way to determine whether or not they are diastereomers or enantiomers or what. So if you do that, you'll quickly find that this one is RS and this one is RR, and therefore they are diastereomers of each other. Okay, now that being said, in the case of the RS molecule, if you rotate this 180 degrees so that this ethyl group is kind of pointing down here, so it's kind of like a reflection of this one, and this methyl group, once you rotate it, will start pointing towards you, and it'll be up here, then you have a mirror plane that cuts through the molecule in this direction. Now, that being said, it is possible to have molecules that don't have rotational symmetry, that don't have a mirror plane, and yet are somehow a chiral. Now, these are a little rarer, and this is kind of a trick problem, so don't stress too much about this, but here's an example of one. If you try drawing the mirror image of this molecule, and you rotated and reflected it, or not reflected, but rotated it and both I guess in the plane of the paper and with a rotational axis that's sticking perpendicular to the paper, you would find that the two molecules are still identical. Okay, now this is kind of hard to do sometimes on paper, but if you can also do this with a handheld model, and that might help too. Okay, so here's what it looks like on paper. So here's this mirror image. If you flip it with horizontally, so imagine an axis running this way from east to west on your paper, and you've rotated it that way. Okay, that's what that looks like. And then imagine that you've got a central point with an axis sticking through the paper, and you rotate this, let's say clockwise or counterclockwise, but just 180 degrees. Now you would get this molecule, which you can see now is identical to the first original molecule. Okay, so again, this is kind of an interesting case where there's neither a mirror plane nor a rotational axis within the molecule, yet it somehow works out. Again, don't stress too much about this. This is kind of a rarer case. Okay, I earlier mentioned carbohydrates. Now, when it comes to designating or kind of illustrating the three-dimensional stereochemistry of the carbons in your carbohydrate, we can do this using what's called a Fischer projection. Okay, now to do this, we take our tetrahedral carbon and we orient the groups coming off of it so that, two of them are pointing towards us, two of them are pointing away from us. And we kind of set the carbon containing groups pointing away from us on the north and south of this intersection. Okay. Now the non-carbon groups are kind of placed at the east and west, and based on the non-hydrogen groups priority, you can essentially assign stereochemistry to these. Okay, so in the case of carbohydrates, you'd see that you can basically, based on the bottom chiral center, you give the carbohydrate a D or an L designation. Okay, so if you've ever heard of dextrose, that's just the D version of glucose. Okay, where the alcohol group on that bottom chiral carbon is pointing to the right. Okay, dextro meaning right. So here's an example of some carbohydrates with those. Okay, so here we have Fischer projections. You can see we've got those intersections, and based on where that chiral carbon or that alcohol group's pointing on that bottom chiral carbon, okay, we can give that designation to our sugar. Okay, so this would be this sugar in the middle here would be a D sugar. This one is an L sugar. Okay, an L carbohydrate. By the way, each of these intersections is a chiral carbon, mind you. Okay, so we show all chiral carbons this way using this sort of intersection in our Fischer projections. Okay. This also makes it really quick and easy to determine whether you have enantiomers or diastereomers. So here you can see that both of your chiral centers have been flipped perfectly. Here the bromines are both are to the right. Here they're both to the left. So that's a perfect mirror image, and therefore these are enantiomers. Here we have two molecules. They are identical for the top carbon, but they are flipped for the bottom carbon, and that makes them diastereomers. So back in the chapter where we learned about rotational conformers, right, where you could rotate around a carbon-carbon bond to get different versions of the same molecule, we saw that we can, get different torsional angles, right? We could get like gauche or anti-interactions. We could have our group staggered or eclipsed. Well, let's look at this gauche, this gauche conformation that we have drawn for butane here. If we draw the mirror image of that, are those two drawings enantiomers? Well, the answer is no, because you can rotate freely around that carbon-carbon bond take that mirror image and recreate the original molecule, right? So in other words, they're identical. They're the same molecule. Okay, so in order to be chiral, we cannot just have a mirror image just be the rotational conformer of another molecule. Okay, we have to have things kind of locked in place somehow. Now, this often comes into play with our ring compounds. We saw some examples with chair structures. We saw, for example, the cyclohexane or the dimethyl cyclohexane molecule having one of its structures kind of get canceled out because it's a meso compound. So its mirror image was an identical molecule, right? How can we figure that out when we're using chair drawings or Haworth projections, right? So with the, you can see here with our Haworth projection, using that sort of bond line diagram and the wedges, we can quickly identify that mirror plane. Whereas in the chair drawing, it's not as obvious. In fact, it's kind of misleading because you can see that this group is axial and this group's equatorial, and you think like, wait a minute, there's no mirror plane in that. How can we do that? Well, in order to see that, we're going to have to do a little bit of ring flipping and seeing how these two things are actually interrelated. Okay, so it's just that you can't see the mirror image in the way this chair conformation is drawn, but you'll see how it effectively applies. So let's have a look. Okay. Basically, if we do a ring flip, this axial group becomes equatorial here, and this equatorial group becomes axial over here. And then if we rotate it 180 degrees, well, now it's the mirror image of the same molecule. So in other words, this molecule is equivalent, is the same as its mirror image, and therefore it is achiral. Okay? So even though there are two chiral centers, and there is no mirror plane within the molecule, this is another example of those molecules where it's not immediately obvious that that there is that it is achiral. That if you do draw the mirror image, it's actually the same molecule, and you can do manipulations to see that. Okay, in this case, though, it involves doing some ring flipping and rotating. Though, of course, the shortcut, again, is to draw it like that Hayward projection, that bond line diagram with the wedges to show, like, that there's clearly a mirror plane in here, making this a meso compound. All right, so how do we separate mixtures of enantiomers? We mentioned earlier that this is kind of difficult because the physical properties of our enantiomers are so similar, right? We mentioned that with the example of R and S carvone, they had the same melting point and boiling point, so we can't use distillation because you need different boiling points for that. We can't use recrystallization. That requires different solubilities, and if these molecules have the same intermolecular forces, which they would, they'll probably have similar solubilities. Okay? So we can't use anything that takes advantage of that melting point either, okay, for the same reason. So basically, this creates a bit of a problem, a little bit of a conundrum here. So the first successful attempt to resolve a mixture of enantiomers was back in 1847. Louis Pasteur, that Louis Pasteur, the one for whom pasteurization is named, basically was able to separate out a racemic mixture of tartaric acid. What he did was he converted it into its salt form, and when he recrystallized it, he found out that the crystal structures were slightly different, and he had to painstakingly separate them by hand using tweezers. Now, this is not practical, obviously, so we need to look for some more practical methods to separate out our enantiomers. So one way to do this is to use what's called a chiral resolving agent. Okay, so basically, it's kind of sort of piggybacking off Louis Pasteur's idea of forming the salt version of your molecule, but in this case, you're going to use a molecule that is itself chiral, but we're going to use only one enantiomer of it. So even though you have a racemic mixture, by reacting it with one enantiomer of a chiral molecule, you wind up making a pair of diastereomers. And now this pair of diastereomers has different physical properties that you can exploit. Another way to do this is to use what's called affinity chromatography. Now, you're actually going to see affinity chromatography in a fashion in lab when you do thin layer chromatography and column chromatography. Basically, you have a particular medium, so we're going to use silica gel or alumina gel, and we're going to pass our mixture with a solvent through that medium. Okay, and based on the polarity of the parts of our mixture, they either stick to that medium or to the solvent a little bit more, and as a result they travel at different rates across the medium. Okay, so in the case of our thin layer chromatography, as our solvent travels up the plate, our spots move down, up the plate at different rates. And so when we're done, the spots will have moved different distances, and that's how we'll be able to tell them apart. Or in the case of column chromatography, when we run our solvent through the column, our solutes basically, because they move at different rates through the column, one solute will reach the end and can be collected first, and then eventually the second one will make its way through and can be collected separately. All right. So we can use a similar concept for chiral molecules, except instead of using just different polarities, we can take beads that have chiral agents attached to them, things that are themselves chiral, and hopefully one enantiomer will stick to this, to these agents a little bit more than the other enantiomer. Okay, and as a result, that'll cause that separation we're looking for. Okay, and that's it for this chapter. So I'll go through the additional practice problems. Of course, feel free to, please attempt the homework problems, and let me know if you have any questions. So first one, just asked to draw any pair of constitutional isomers. Again, there's an infinity of possibilities here. Just make sure you pick two things that have the same molecular formula, but would have different names if you drew them using, if you name them using IUPAC rules. So for example, here is butane on the right and 2,2-dimethylpropane. Both of them have the, actually, sorry, 1, 2, 3, 4. 2, 3, 4, 5. Oh, there's 2, 3, 4. Yeah, this slide's actually wrong. So just to fix this, I think they left out a carbon on the molecule on the right. So if we look at this molecule on the left, this is 1, 2, 3, 4, 5. There's 5 carbons. This is C5H12. Okay, this is 2,2-dimethylpropane. I think they meant to have pentane drawn here, so there should have been an extra line here to give it the formula C5H12. But in any case, yeah, that would be an example of two constitutional isomers. They would both be C5H12, but clearly their names are different because the atoms are connected differently. Instead of having 5 carbons connected in a row, here we have 3 in a row, and then the remaining 2 branch off the middle carbon. All right, cis-trans isomers. Again, you've got a whole bunch of possibilities here. You could draw an alkene where the carbon-carbon double bond's locked in place, and so you can just draw 2 identical groups on opposite sides of that double bond or on the same side. Or likewise, we could have a cyclohexane and draw 2 groups that are on the same side or on opposite sides of that ring. So here are both examples. Okay, so here on the left we have, so here's a trans alkene. These methyl groups are on opposite sides of the double bond. And here the methyl groups are on the same side of the double bond. Here we have a trans dimethylcyclopentane. So it's 1,3 trans 1,3-dimethylcyclopentane. This group is pointing away from you. This group is pointing towards you. Here, both groups are pointing in the same direction. They're both pointing towards you. So that's why that's the cis isomer. Okay. To draw a pair of diastereomers that are not cis-trans isomers, a good example here would be if you had, here we have 2 chiral centers. Here, instead of flipping both chiral centers, so instead of, like here we have 2 wedges, 2 solid wedges. If you wanted the enantiomer of this, you would make both of these dashed wedges. So if you only flip one of them but leave the other one the same, now these are diastereomers. Okay, so keep that in mind. One example of diastereomers is if you have multiple chiral centers but don't flip all of them. Okay. In the case of enantiomers, they have to be non-superimposable mirror images. So, again, look for a chiral center and just make sure you flip it. Okay, so here's an example where we've flipped both chiral centers to be dashed dashed wedges. So compare that to this molecule where you've got solid wedges. Again, you could also draw it just by drawing the mirror image as they've done here. So drawing molecule B here, you could draw it either way and you'd still be correct. That's still the enantiomer of molecule A. All right, 3 chiral centers. Again, you've got lots of options here. So this is just one example they've got here. Okay, so here's our 3 chiral centers, but there's lots of molecules with 3 chiral centers. Okay. Now you want to be careful a little bit with having too much symmetry. So if this chlorine were also an OH group, this carbon would not be chiral anymore because this pathway, this group and this group would be identical. So that's why they had a chlorine here instead of an OH group. So something to keep in mind. All right, have a look at this molecule and label the chiral centers here. So feel free to pause here to give yourself some more think time. Okay. So this molecule has a little less chirality than you'd think. Again, remember, as soon as you see 2 identical groups attached to your carbon, you know that it can't be chiral. Okay, so in this case, these 2 carbons here have 2 methyl groups each attached to them. As soon as you see a methyl group here and a methyl group here, that carbon can't be chiral. Likewise here, methyl group here and here, that carbon can't be chiral. I think what throws off students here is when they see the geometry of this. They see this carbon's in the plane of the paper, this one's sticking out towards you, or this one's sticking away from you. That doesn't matter. Remember, you've got rotation, free rotation around this bond. So it's drawn that way with this methyl group pointing towards you, but that need not be the case. Okay, the important thing is that this is a methyl group, this is a methyl group, that carbon can't be chiral. Okay, so in the previous problem we saw that these 2 carbons are chiral. Okay, and so go ahead and try and designate them as R or S. So look at the 4 groups attached, assign them priorities, and go from there. Okay, so they both have S designations. Okay, so in this case the hydrogen that's not shown is pointing away from you. We assign highest priority to this carbon because it's it's got 2 carbons and a hydrogen attached to it. Next priority is this one. It's got a carbon and 2 hydrogens attached to it. And then third priority is this carbon, which has only 3 hydrogens attached to it. So looking at those, it's going counterclockwise, so it's the S designation. Okay, and then with looking at this carbon, it's similar. It's kind of similar observation. It looks like it's an R designation, but keep in mind that the hydrogen is pointing towards you, so you're actually looking at this backwards. So even though it looks like it's going clockwise, really you're looking at it backwards, and it should be going counterclockwise. All right, here is a specific rotation problem. So they tell you that the R enantiomer of a particular pair of enantiomers has a specific rotation of plus 33 degrees. Now, they tell you that you have a mixture that has 56% of the S enantiomer and 44% of the R enantiomer, and they ask you what the rotation will be. So what's the alpha for this mixture? Okay, so when you're trying to do this problem, I would first recommend trying to find the enantiomeric excess. Since the question gives you the ratio of R to S, you should be able to figure that out pretty easily. Okay. Once you do that, then you can plug it into that formula for an enantiomeric excess, relating enantiomeric excess with specific rotation. So remember, it's the specific rotation of your sample divided by the specific rotation of the pure enantiomer times 100. Now, please note that there's going to be this problem is a little tricky in that it gives you the specific rotation of one enantiomer, but it turns out that that enantiomer is not the majority of your mixture. So something to keep in mind. Okay, so feel free to pause this and try this out. So if you have 56% of the S enantiomer, well, that means you have a 12% enantiomeric excess of S. Okay, so in other words, the pure enantiomer we're going to use is the S enantiomer. Well, if the R enantiomer has a specific rotation of plus 33 degrees, then the S enantiomer will have a specific rotation of negative 33 degrees. So we take, basically, we're going to take our observed, um, so if we know that this is 12% and this is negative 33, we're going to solve for the observed A. Okay, so take 12% times negative 33, divide by 100, and that gives you the answer. Now let's have a look at these two molecules and see if you can see the relationship between the two of them. Okay, so these are actually identical molecules, and if it's kind of hard to see, basically try to, if you flip this molecule over, if you kind of rotate it using this axis that I'm making, so if you kind of rotate it this way, so this point is to the right, this cluster over here starts pointing towards you instead of away from you. And likewise, this methyl group points away from you and not towards you. Well, that's the same as this molecule here. Again, if you're having trouble seeing that, especially trying to visualize that in 3D, one way to do this is to just assign R and S configurations to these two chiral centers. And you'll see that the chirality is the same for both, for in both molecules. So the designation, the Kahn-Ingold pre-log designation here will be the same for the one here. And likewise, this carbon here will be the same as this one here. And that's how you can tell they're identical molecules. And that's it for this chapter. So again, if you have any questions, please let me know. And be sure to try the homework and any extra practice problems.